Right, in this video I'm going to run through the questions that you need. From CC9 you are being tested on concentration and empirical formula, and then from CC16 it's mostly on combustion, which we've just done. So the first question, they ask you to calculate concentration. They tell you concentration is mass divided by volume, and they ask that you give your answer in grams per decimeters cubed. Mass is obviously in grams, so you need something in grams divided by something in decimeters cubed, which represents a volume. Now if you look at the numbers that you're given, 9.25 grams, that's fine. So I can write concentration equals 9.25 grams divided by, but the volume I need in decimeters cubed, and they tell me here that my volume is in centimeters cubed. That means I need to convert from centimeters cubed to decimeters cubed. So to get from one to the other, all I need to do is divide by 1000. So instead of dividing this by 200, I'm dividing this by 0.2, which is decimeters cubed. Now I've got something in grams divided by something in decimeters cubed, and that's going to be my answer. So it's 9.25 divided by 0.2, and the answer works out as being 46.25. The next question, all right, they don't give you the actual formula this time, but if you look at the units give you the formula. Whatever comes first goes into your calculator first, and whatever second goes in second. So it's grams divided by decimeters cubed, all right? So again, I've got something in grams, 23.5 grams, so that goes into my formula straight away. But if I look again, I don't have decimeters cubed, I've got centimeters cubed. I need to divide that number by 1000. When I do that, I get 0.250 decimeters cubed, and then it's grams divided by decimeters cubed, and my final answer is going to be 94 grams per decimeters cubed. Okay, so there are two on concentration. The next one is on empirical formula. Okay, so you'll see here empirical formula. When you're doing empirical formula, you're going to do a similar table to what we were doing last week. So they tell me I've got element A and I've got element G. So I'm going to put A and G, and then I've got G, Mr, moles, and ratio. The G for A is 3.5. The G for G is 4.0. The formula mass, they tell you A is 7. They tell you G is 16. And then you work out moles by doing G divided by MR. So the first one is, the first one is going to work out as 0.5, and the second one works out as 0.25. Now at this point, okay, unlike in the questions we were doing last week where you had a balanced chemical equation and you use that to find the ratio, in this case you're going to use moles to work out what the ratio is. And to do this, you're going to divide both of these by the smallest number. You've got 0.5, 0.25. 0.25 is smaller than 0.5, so I divide both numbers by 0.25. And when I do that, I get 1 and I get 2. And this ratio here, I can then use to write a formula. And this bit is critical. If you don't do this, you lose the last mark. A is on the same side as 2, so I draw my A and I use a little 2, it's always a small number, and then G is on the same side as the 1, so I would have a little 1, although you don't need to have the little 1. That's empirical formula. And the next page, I'm going to come back to that one in a second. I want to do another empirical formula one first. Do I not have another empirical formula one? Maybe I don't. I do. I'm going to swip over here to page 25. I'm just going to do the other empirical formula one first. So, oh, it's because my pages are in the wrong order. Sorry, that's been happening recently. They print them in the wrong order. Right, so now I'm on question 25, which is where I want to be. It asks you for the meaning of the term empirical formula. You need to learn it. Simplest ratio of atoms of each element in a substance. I'd actually go a little bit further than that. I'd say simplest whole number ratio, because you can't have the ratio in decimal places. Simplest whole number ratio of atoms in a substance is enough there. So just learn that, it's on carousel. This next one here, finding empirical formula. So I've got sulfur and I've got fluorine. Okay, so I write S and I write F. Now you don't have to worry about things being diatomic in this case. elements are only diatomic when they are elements, and these have reacted with each other. If they're not elements, you don't need to worry about diatomics. I'm just going to write S and F. I'm going to write G Mr. moles ratio. The G for fluorine is 17.1. The G for sulfur is 4.8. And just make sure that you put those on the wrong side. If you have them the wrong way around, you're going to be wrong right from the start. This is 19. This is 32. All right, so I'm getting 19 there, 32 there. Again, I'm dividing. When I divide this by this, I get an answer of 0.15. Actually, this is the one that came up in your mock. 17.1 divided by 19 is 0.9. Okay, so that's moles. Which one of these numbers is smaller? 15 is smaller than 0.90, so 15 is smaller than 90. So I'm dividing both of them by 15, and I get an answer of 1 is to 6. And then to finish it off, I have to write S. All right, it's just with a little 1. You don't need the 1, but and then I write F and I write a little 6. SF6. That is my empirical formula. One other empirical formula one here, 26. This time I've got sodium and I've got oxygen. Again, it doesn't matter that it's diatomic. It's not an element. It has reacted with sodium. So I do G Mr. moles ratio. The G for sodium, 0.92. The G for oxygen, 0.32. The MR for sodium is 23. The MR for oxygen is 16. Before you go any further, just make sure you put the numbers in the right place. I divide and I get 0.04 for sodium. I divide here and I get 0.02. 0.02 is smaller than 0.04. I divide both of them by the smallest number. I get 1 is to 2. And then my answer is Na with a little 2 and then O with a little 1. Okay, so that is empirical formula. I'm going to go back and do, oh, they're all over the place. Sorry, I've got another 2 concentration ones here, which I have skipped because the numbers in the wrong order, so I'll go back and I'll do these ones. So calculate the concentration of the solution in grams per decimeter cubed. So again, if it's concentration, it's whatever in grams, 28.4 grams divided by whatever is in decimeter cubed. Again, you're given something in centimeters cubed instead, so 0.250. I divide it by 1,000 to put it into decimeters cubed, and once I do that, I get 114. Question number 24. This one's slightly different. It asks you to calculate the number of moles in 50 centimeters cubed of this solution. So you're given the concentration in grams per decimeters cubed, and then you're asked to calculate the number of moles in 50 centimeters cubed. So you're given a concentration, you're given a volume, and you're asked for moles. All right, so if we look at the formula triangle that we had, that you do need to learn, they gave it to you back here. All right, you've got G at the top, and then you've got concentration and you've got volume. All right, so I've got grams at the top, I've got concentration, and I've got volume. So using this formula triangle, all right, they've given me concentration, they've given me volume, I'm going to be able to find grams, and once I've got grams, I'm going to be able to find moles using G Mr. moles. Okay, but I need to find grams first. So grams is going to equal concentration times volume. All right, using my formula triangle, concentration times volume. The concentration, they tell me, is 15.85, and that's in grams per decimeters cubed. The volume they give me is in centimeters cubed, and this is important because they've given me concentration per decimeters cubed. I need to put my volume into decimeters cubed before I can plug it into my equation. Okay, and to go from centimeters cubed to decimeters cubed, we've seen this already, you just divide by 1,000, so that's going to become 0.05. So it is 0.05 times 15.85. and I work out the number of grams, 0.7925. That's the number of grams that I've got of my copper sulfate. Okay, now I need to switch triangles. G Mr. moles, they're asking me for moles. I've got grams, I can work out formula mass. So if I work out formula mass of copper sulfate, okay, copper is 63.5, sulfur, they tell me, is 32, and oxygen is 16, and I've got 4 oxygens. It's CuSO4, so it's going to be 16 times 4. And when I work all that out, I get 159.5. They've asked me to work out moles, so moles equals Mass, which I've just worked out over here, 0.7925 divided by MR 159.5. And when I work that out, my final answer is going to be 0.005. At least I hope it is. Divided by 159.5 equals, yes, 0.005 moles, and that is my final answer. All right, so that one is a little bit trickier, but even if you're not entirely sure what to do, like find formula mass. Okay, you know you're trying to find moles. Ultimately they give you these numbers, find formula mass, that gets you a mark, and then just try and do something with the numbers, because it's worth 3 marks. You get error carry forward, try not to leave it blank. Few other calculations to do. All right, I'm going to come back to this one. I'm going to come back to this one first. 29. Determine the formula. So this is, again, it's just, it doesn't say the word empirical, but that's what it means, empirical formula. So this one's the same as before. So I've got iron, I've got oxygen. Again, doesn't matter that it's diatomic because it is not an element after it's reacted. Grams of iron 2.24, oxygen 0.96, MR of iron 56, MR of oxygen 16. Again, make sure you put those numbers in the right order. And when I divide, I get 0.04 here, and I get 0.06. 0.04 is smaller, so I divide everything by 0.04, and I end up with a ratio of 1:1.5. Actually, we haven't had this before. 1:1.5. Okay, so my answers need to be whole numbers, and after ending up with 0.5. And the temptation here is just to round it up. Go 1.5 is the same as 2, but you cannot do that. Okay, you can't round 0.5 all the way up to 2. So instead, 0.5 represents a half. If I want to make a half a whole, I need to multiply by 2, because there are 2 halves in a whole. So if I do 1.5 times 2, I'm going to get a whole number. I'm going to get 3. But if I multiply the right hand side by 2, I also have to multiply the left hand side by 2, and I get a ratio of 2:3. So 2:3 is the same ratio as 1:1.5. I've kept the same relationship between them, but by multiplying by 2, I've gotten rid of the decimal place, and I knew to multiply by 2 because 0.5 is a half and 2 halves make a whole. Okay, if they gave you 0.25, 0.25 is a quarter, there are 4 quarters in a whole, I would multiply by 4. If they gave you 0.33, 0.33 is a third, there are 3 thirds in a whole, so I'd multiply by 3. Okay, so what this tells me is that the formula of iron oxide is Fe2O3, Fe2O. Then it asks you to fill it into this equation, because now you know the formula of iron oxide, and once you've got it filled in, you can go back and you can balance. It's actually an awkward one to balance, not going to lie. So I've got 2 oxygens on the left, 3 on the right. When I've got a 2 and a 3, I need to make them both 6. So to make them 6, because 6 is the lowest number that 2 and 3 both divide into evenly, to make them both 6, I need a big 2 here, because 2 multiplied by 3 is 6. And then over here I need a 3, because 3 multiplied by 2 is 6. So now I've got 6 oxygens on each side. But if I look at iron, I've got 2 multiplied by 2 is 4, so I need a big 4 there. So the last mark goes for balancing the equation, but all of the other marks are just going from doing empirical formula, and that I feel that you can definitely do and get those 3 marks. I'm going to go back to question 28. Now, question 28. This one is on molecular formula. All right, now for molecular formula, you're going to need to find empirical formula first. So we'll do that first, and once we've got empirical formula, I will show you what to do with it. All right, so I'm going to find empirical formula first. I've got phosphorus, I've got oxygen, I've got G Mr. moles ratio. The G of phosphorus 1.24, the G of oxygen 1.60, MR of phosphorus 31, MR of oxygen 16. I do the division and I get 0.04 and I get 0.1. Smallest is 0.04. all right, that 0 obviously makes it smaller, so if I divide by that and divide by that, I get 1 is to, what does it work out as 0.1 divided by 0.04, Oh, I get 1 is to 2.5. It's the same as what we've just seen. If you end up with a 0.5, to get rid of it, you have to times it by 2, because 0.5 is a half, and 2 halves in a whole. So 2 times 2.5 is 5, 2 times 1 is 2. So my ratio is 2 is to 5, and that means my empirical formula is P2, all right, and O5. That is my empirical formula. But in this case, you were asked for the molecular formula. And just to show you the difference, all right, the empirical formula is the simplest whole number ratio. So just say I had a formula that was like this, C6H12O6, okay, glucose. This here represents the molecular formula of glucose. It tells me exactly how many atoms are in glucose. I've got 6 carbons, 12 hydrogens, and 6 oxygens. But these numbers can be simplified. I divide each of these numbers by 6. I get CH2O, and this represents the empirical formula. So empirical is the simplest whole number ratio. So you can see from your molecular formula, you've got the same number of carbons and oxygens. In the empirical formula, that's still true. And I can see that I've got double the number of hydrogens. I've got 12 compared to 6. And in the empirical formula, that's still true, 2 compared to 1. So the ratios are the same in the molecular and the empirical formula, but molecular shows me the actual number of atoms, whereas the empirical shows me just the simplest ratio. It's a 1 is to 2 ratio instead of having it as 6 is to 12. In this question, you're asked to work out the molecular formula. So how many atoms do we actually have in phosphorus oxide? I've worked out the empirical, so I've worked out the simplest ratio, but I don't know if this is the molecular formula. There could be more phosphorus and more oxygen. They just have to keep a 2 is to 5 ratio. So to work this out, once I've got the empirical formula, okay, you need to do 3 steps. Step 1 is to work out the formula mass of the empirical formula. My empirical formula is P2O5, so I work out the formula mass of P2O5. So I've got 2 phosphorus, which is going to be 31 plus 31, and I've got 5 oxygens, which is going to be 16 times 5 of them. I add all that up and I get 142. All right. Step 2 is they're going to give you another number in the question. Okay, they give you the relative formula mass of the phosphorus oxide, 284. And I take the number that they give me in the question and I divide it by my answer to step 1. So 284 divided by 142, and I get an answer of 2. All right, so this is step 1. This is step 2. So step 1, find the formula mass of the empirical formula. Step 2, the number in the question divided by your answer to step 1. And then step 3, you take your answer to step 2 and you multiply it by your empirical formula. 2 times 2 is 4, so I have P4. 2 times 5 is 10, O10. P4O10, that is my molecular formula. So this is the actual number of atoms I've got. But if I simplify that ratio, I can get down to 2 is to 5. What other question have I not done? Oh, Christ alive. So many. Right, question 30. Actually, this isn't as bad as I initially thought. Okay. An experiment found that 4.4 reacted with excess to form 24.84 of lead. Carry out a calculation using it to show which equation represents the reaction taking place. Okay, so I've got iron, and they tell me I have got G. Even if you don't know where you're going with this, right? Do your G Mr. moles, okay? They've given you 4.48 grams of iron, okay? They tell you that iron is 56. At least work out the number of moles of iron. They give you mass, they give you Mr. Work out the number of moles of iron, and you are going to get 0.08, all right? You can do the same for lead. Lead is Pb. They've given you mass. They've given you formula mass. Again, you can work out Mr. 0.12. And once you've got both of these, simplify the ratio just like we did before. Smallest number is 0.08. Divide by 0.08 and you get an answer of 1 is to 1.5, I think. Yes, it will go in 1.5 times. All right. Again, can't have a fraction. Sorry, decimal, multiply everything by 2 and I get a ratio of 2 is to 3. okay? And what this ratio is telling me is that I should have a ratio of 2:3 between the iron and the lead when they're reacting. If I go back up and look at my equations, in equation 2, I've got a 2 in front of the iron, and I've got a 3 here in front of the, oh no wait, they're asking me it's the lead. I need a 2 in front of the iron, and I need a 3 in front of the lead that we are forming. And that's exactly what I've got in equation 2. I've got a ratio of 2:3, and I've got that ratio of 2:3. If you look at equation 1, you've got a ratio of 1:1, and that doesn't match the calculation we've just done. So I've carried out a calculation, and I've used that information to work out that it must be equation 2 that fits my calculation. So all I have to write is equation 2 is correct. Equation 2 is correct. So even if you weren't sure what you were doing, you're given mass of both. You can work out moles of both. Once you've drawn out this table, just do what you always do, simplify the ratio, and then which equation does this ratio fit? A 2 with the iron, a 3 with the lead, it fits equation 2, and that's essentially all you're doing. It's a different style of question than what they usually ask, but a similar, but it builds on a method that you are familiar with. This one's exactly the same. All right, so we get to practice it again. So I've got iron, and I've got chlorine. I've got 8.4 of iron. In an experiment, iron reacts with chlorine to form iron chloride. All right, so I need to pay attention to what information they're actually giving me. So I've got the iron, and I've got iron chloride. Now, there are two formulas for iron chloride. I've got FeCl2 and I've got FeCl3, and I don't know which one is correct at this point, okay? I'm just going to take FeCl2, and I'm going to see if it works out. And if it doesn't work out nicely for me, then I'm going to know the answer is FeCl3. Okay, so it's just a bit of trial and error. So I'm going to take 19.05 here. Okay, I'm going to take FeCl2. I've got G, Mr, moles, ratio. The Mr for iron is just going to be 56. The Mr for iron chloride, you've got 56 for the iron, and you've got 2 chlorine, so it's 35.5 times 2. And if I work that out, which we're going to have to do here, 35.5 times 2, 71, plus 56 is 127. All right, so now I do 8.40 divided by 56, and I get 0.15. And then I do my 19.05 divided by 127 equals 0.15. Okay, now they're both exactly the same, which means my ratio is 1:1. And now I need to go back and look if that's correct. Do I have a 1:1 ratio between iron and FeCl2? There's no number in front of iron, so it's a 1. There's no number in front of FeCl2, so it's a 1. So the calculation I've just done matches A. So I would then say the calculation I've done matches A, therefore the answer is A. Equation A represents the reaction. And if you had chosen FeCl3, you'll find that the numbers won't fit the equation, and then you'll know that it's not the right answer. If B doesn't work, then it must be A. So you can either prove that A is correct, or if you try B, you can show that it's incorrect, and therefore the answer must be A. But you just need to show the workings for either. You don't need to show the workings for both. Right, that's all the calculations done. A few questions now on combustion. All right, so when you combust a hydrocarbon, okay, that's what you're doing here. You are burning a hydrocarbon, so you're combusting a hydrocarbon, and we know we make CO2 and we make H2O every single time. But this is set up to show that you're actually making these two products. All right, so you're going to initially make water vapor. It's going to be a gas. CO2 is always a gas. Those products are going to come along this tube, and they're going to come in here into this beaker of ice. And once they come into the ice, the water is going to cool down, and the water is going to condense. So you're going to see liquid water forming at the bottom of tube A. The carbon dioxide is going to keep going. It's going to end up here in the indicator solution. Carbon dioxide is acidic, and because it's acidic, in the indicator solution, you're going to see a change of color, okay, which is what it tells you down here. So it asks you to explain these observations. And the other thing is that the funnel becomes hot, okay? So of course this funnel is going to become hot because you are burning something, okay? And if you're burning something, you've got an exothermic reaction, it releases heat. So to explain why the funnel becomes hot, you're just going to say that heat is released, or it's an exothermic reaction. To explain why you end up forming a liquid, you're going to say that that water condenses to form the liquid. And to say why your indicator changes, you're going to say it's because the carbon dioxide has been produced, and carbon dioxide is an acidic gas. On the other side, fraction that's easiest to ignite, remember the easiest to ignite at the top, so gases is going to be your answer there. The least viscous, okay, they get more viscous as you go down the column, so the one closest to the top will be the least viscous, and of the ones they've given you, petrol is closest to the top, so petrol is the least viscous. They don't have to give you this in order though, you do need to learn it. Contains sulfur as an impurity. All right, when you're burning something, you're reacting it with oxygen. If you've got some sulfur in your hydrocarbon fuel and you burn your fuel, you'll also burn the sulfur. You'll react the sulfur with oxygen and you're going to form sulfur dioxide. Okay, once you form that sulfur dioxide, it can dissolve in rain, and when it dissolves in rain, it forms acid rain. Dissolves in rain, forms acid rain. And how does acid rain cause problems to the environment? You can say it kills fish, you can say it kills plants, you can say it damages buildings, although to be honest, when it says environment, I would always pick something living. So I talk about plants, talk about fish, the effects of acid rain on the environment. I know there's a 6 marker. It's really not difficult. Methane is a fuel burnt in gas-fired boilers. Why is it important that there's plenty of air? All right, so what this is asking you, when you've got plenty of air, you get complete combustion. When you don't have plenty of air, you get incomplete combustion. They're asking you, why is it important that you get complete combustion instead of incomplete combustion? Okay, so your answer to this is you're going to say plenty of air leads to complete combustion. Complete combustion forms carbon dioxide and it forms water. Not a lot of air leads to incomplete combustion. Incomplete combustion forms carbon monoxide and forms soot. Then you need to tell me what's wrong with that. Carbon monoxide is a toxic gas. Okay, it can literally kill you. You can't see it, you can't smell it, you can't taste it, so it's very dangerous. And you can also say that the soot produced can cause breathing problems. Okay, so just tell me that incomplete combustion will occur if you don't have a lot of air, and incomplete combustion is bad because of the carbon monoxide and because of the soot, and tell me why it's bad. God, this video's getting long. Right, last question. Which statement about the members of the alkane homologous series is correct? They don't show a trend in chemical properties. Showing a trend suggests that they change slightly. They all react in the same way, so it's not a trend in chemical properties. Their boiling points decreases as the molecules get larger. That's incorrect. Okay, as they get bigger, the intermolecular forces get stronger, so their boiling points will increase. The molecular formula of neighbouring compounds differ by CH3. They don't differ by CH3, it differs by CH2, so that's incorrect. And their viscosity increases as the molecule gets larger. That is true. As they get bigger, intermolecular forces get stronger, they become more viscous, they become harder to pour because the particles are harder to separate. Which one runs the same homologous series? C8H18. So this must be an alkane because I double the number of carbons and I add 2. So double 8 is 16, add 2 is 18. So I need to find another one which I double and then add 2, and that's going to be C. Double 4 is 8, add 2 is 10. Write in a balanced equation for combustion of octane C8H18. If it's combustion, you're reacting it with oxygen, you are going to form CO2 and H2O because it's complete combustion. You get 2 marks just for that. Then you need to balance it. It is tricky to balance this one. Carbon first, 8 carbons, 18 hydrogens. I need a 9 there. 9 times 2 is 18. And if I add up the oxygens, 8 times 2, I've got 16 oxygens from the CO2. 9 times 1, I've got 9 oxygens from the H2O. 16 plus 9, I've got 25 oxygens. I need to get 25 oxygens over here. If you just do 25 over 2, okay, so you're going to have to use a fraction or you're going to have to use a decimal. So you can write it as 25 over 2, or you can write it as 12.5, because 12.5 times 2 is 25, and that matches. So you can use a decimal and you can use a fraction if needed. Ugh.